Okay, so this one was a bit of a modelling with a first order differential equation question. We've got lots of information and they want us to write down an expression for the total volume of water in the container at time t. So let's have a look. So it starts with 3 litres and we want this in terms of litres. So initially we've got 3 litres. Water goes in, well, contaminated water goes in at a rate of 250 millilitres per minute. So is time measured in minutes? Yes, it is. Okay. So we have 3 litres, and then at time t, we have water coming in at a rate of 0.25 litres per minute. Okay, so that's that bit, and then the container is drained, so that's water going out. Whoops, at a rate of 0.125 T per minute. There's nothing else to do with the change in the level of liquid, so if we simplify that, we get 3 plus 0.125 T. So that's going to be our volume. Right, and then we're going to go on and write an equation about the amount of contaminant in the container. So we want to know a differential equation, so we want to know the rate of change of the contaminant. So what's going to be the rate of change? So we need to look at contaminant in. So how much is coming in? So let's have a look. The amount of contaminant in the water pouring into the container at time t minutes is modelled to be this much per litre. So we're going to have that expression, but there's not 1 litre coming in, it's coming in at a rate of 250 millilitres, so I need to times that by a quarter. Okay, meanwhile, some contaminant will also be leaking out. So M is the amount in the container at time t. So that's how much we've got in the container in milligrams. So how much is going to be coming out? Well, that's dispersed throughout the whole container. So we've got that per milligram, and how much liquid have we got in the container? So we've got 3 plus 0.125 T litres in the container at a time. And how much goes out? 0.125. So both of these are the rate in milligrams per minute that the contaminant is going in and out. So the rate of change is how much is coming in subtract how much is going out. So if I change 0.125 to an eighth, okay, and then I can just simplify this expression. So that's 5 minus E which is what they were looking for. Okay, now they ask us to solve the differential equation. So I'll just rewrite the differential equation here. Right, so this is a first order differential equation, so what would you usually do with that? Let's put this in a form we know how to solve. Okay, so this is now in the form where we've got dm dt plus p times n equals q, where p and q are functions of t. Okay, so that means it's in a form where we can use an integrating factor. So our integrating factor is e, the integral of p, in this case dt, which is e integral, so what's in front of m, so that's going to be 1 over 24 plus t. Now, relatively often you will find that your integrating factor integrates to a ln and then cancels out with the e. So I would be quite confident that that's correct if I did this in the exam. Okay, so I'm then going to multiply by my integrating factor. Not forgetting to multiply both sides by my integrating factor. Okay, and then let's move it out of the way, it's for later question. Now, what's happened here is the left-hand side is now quite easy to integrate. I've got dm dt in m, and I've got this expression, and that's in 1 there. So this is going to integrate to 24 plus t times m. But what's happened is on this side, this is actually looks a lot more complicated now. Now you've got two choices. You can multiply that out and then integrate it, or you could integrate it as it is. Whichever way you do it, you're going to end up using integration by parts. So if you expand it, you end up having to do integration by parts on t e to the minus 0.1t. Or we could just do it directly from here. In the mark scheme they expand first, but you could just do it directly, so I'll do that. So I can have u is 24 plus t, dv dt is going to be 5 minus e to the negative 0.1t. So remembering u is usually what we think of as the simpler one, the one that when we differentiate reduces in terms. Just be careful when you're integrating with the e with all the negatives. Okay. Right, and remembering everything's going to be times a quarter. So uv minus the integral of v du. Okay, and then don't forget, once you've finished integrating, put your constant of integration in. Once you've done that, you can expand and simplify everything. You should be able to get yours into a simpler form. Plus we need to find c, so don't forget to find c, because we actually have enough information to do that. And what we do is go all the way back to the question, and it said right at the top, initially contains 3 litres of pure water. Okay? So to find c, when t equals 0, then we've got that the amount of contaminant is 0, because it initially contains 3 litres of pure water. If you sub all that in, you get 0 equals quite a lot of terms that are 0, but you should be able to get 85 plus c, so c is negative 85. That's yeah, I think that's after we divide by quarter, so I've sort of skipped a few steps. and haven't sorted out all the terms to do with divided by a quarter, but you should eventually be able to get to that. And then you can rearrange your expression. Now just check in the question, yeah, it wanted expression for the amount of contaminant, so that's M. So you do need to then rearrange your expression to get to M. And a kind of fully expanded and simplified version is this. And if you expand and simplify rather than just leave it as it is, okay, so that's what you should be able to get your answer to expand and simplify to. Okay, we then had another question about assessing our model. Okay, so just give us a bit more space there. Right, so now they've given us some information. So after 30 minutes, now time was measured in minutes, so this is T. The concentration was measured as this. So what we need to do is we need to find out what the concentration is for the model. So when T equals 30, we need two bits of information. We need the amount of contaminant, which was N, and we need the volume of water, volume of water in the container. So M, we just get by putting T equals 30 into our expression for M, and you should be able to get 25.65. 677 and some more numbers. Then V you get from this expression. Now this was our answer to the very first question, part 1. So if you substitute into that one, you should get your volume is 6.75. And so our concentration, according to the model, is the amount we've got by the amount of water, which is 3.80 to 3 significant figures. Now, the amount that was measured is 3.79. So as you can see, those two things are very close, so we can conclude that they're very close, so the model is suitable for this time frame. And all I've done for this one is copy what it says in the mark scheme, which you can read here. You just got to say something similar to that.